What is cupric?
2+.
Yeah. Cupric, the IC ending is always the higher oxidation state. A lot of things are 2,3, some are 2,4. It's like tin and lead are 2,4. Copper's really weird. It's the only one that I think that's 1,2. So cuprous would be 1, cupric is 2. And is that a solid? I think that's aqueous, yeah. Again, that's like instead of looking it up first, take a guess. And excess ammonia, so that's important, excess. Now when it says excess in the molecular equation, we don't write out anything special. But it lets us know that there's going to be a lot, so whatever does react will push us, and like I was saying, it'll push us more towards I guess it's also a hint that there might be a complex ion. So you can check your solubility rules first. There's nothing here that could form a solid, so we're going to get some sort of complex ion. And it's not going to be copper and sulfur, but it could be copper and ammonium, which is at the top, or ammonia. H3, and there's 4 of those, and that's a 2+. Balance that out. And then the complete. You really only need to write the net ionic equations for this, but if you write out the complete ionic equations, I won't dock you points if you don't write aqueous. But you should write in what is not aqueous. So we kind of just, on a complete ionic, we can assume if it doesn't have a state symbol, we're assuming that it's aqueous. If it does have a state symbol, then it's not. Oh, I forgot state symbols up here. So sulfate's the same. And then circle that net ionic. If you have large handwriting and you want to do most of the work on another page, just write on the ones where you actually do the work on another page and put the net ionic here.
Do I have to do the complete ionic?
No.
Okay, because I'm able just to go from the base to the net. So.
Yeah, if you can go just from the base, like molecular equation to the net ionic equation, that's fine. Any other questions? on to the next. So on this one, cupric sulfate again, so same, or very similar start. Except now it's a small amount of ammonia. And that's important because our complex ions only form at high concentrations. And that's partly because, like, especially for something like copper, it's not one step. So like when copper is forming these ligands and this complex ions, it's going to be copper 2 plus, and then it adds an NH3, and then it goes to copper, well, actually, wait, I need to write that. NH3, and that's a 2 plus, and then it reacts with another one. And we haven't quite gotten to this in acids and bases. Let me see that. But something like H2SO4, is H2SO4 a strong acid or a weak acid? Strong acid. And when we say it's a strong acid, we mean that, at least for the first hydrogen, it almost completely dissociates. But what about the second hydrogen? Or I guess bisulfate? Is that a strong or a weak acid? It's actually a weak acid. It's also amphoteric because it could act as a base, but when it loses that other hydrogen, H plus plus SO4 2 minus, almost none of the hydrogen sulfate goes on to lose that second hydrogen. And so it happens in steps. So actually the next chapter that we're going to do is how do we actually calculate how much dissociates at those different steps. And so it's the same thing with ligands, except we're just doing it in reverse, right? So it might be really easy to add the first ligand, it's harder to add the second ligand, the third ligand, but it happens in steps. So you need to have enough of the ligand, in this case this would be the ligand, you need to have enough of the ligand present in order to even form the complex ion. Generally a lot. So we look at this next problem. It says a small amount of ammonia and I guess there's two ways you could be thinking about this now. It's like it could be no reaction because the other one was a reaction. But then I said, don't assume it's not a reaction. Because what else could happen with ammonia? And in all of these, we can also assume that there's water because it's aqueous. What does ammonia do with water? NH4OH. So this can make hydroxide, or NH4 plus OH minus. Ooh. And then we could do copper hydroxide. Is that going to be, take a guess, soluble or insoluble? I happen to know for this one. But taking the guess is important But if we go look at our solubility rules, copper and hydroxides are generally insoluble. So we say, oh, that's, so we might guess at first, oh, maybe it's aqueous, and then we go check, and we say, oh, just kidding, soluble. And what does that leave us with? That leaves us with our NH4 and SO4 2 minus, or it is a 2 minus, but balance that. So copper plus lost my train of thought. Two NH3. Plus 2 H2O. So if it's excess, think complex ion. If it's a small amount, then probably not going to be complex ion. Any questions? I think just in case you don't notice it until later, right? Like this is essentially the same reaction. The only difference is a small amount versus excess. Otherwise, it's copper sulfate, cupric sulfate reacting with ammonia. The sort of major product depends on concentration. All right. Let's look at this next one. Anything weird about this one?
Lots of acetic acid. Fair amount of acetic acid, or just acetate.
Yeah. We've got three things. We've got sodium plus sodium acetate. Oops, should have started more to the left. Yeah, so I guess having like the acetic acid plus the sodium acetate might make you think, oh, maybe that's like adding a lot of acetate. But if you go and look at the complex ions,
It's not.
we don't have like, there's like a lead acetate, and that's the only acetate, yeah. But we don't have any lead in this reaction. So what things are going to react here? Mm-hmm. Yeah. So the hydroxide can react with the acid and we get water. And then two sodium acetates. So if we write out like the complete ionic, we got Na plus, we got no H minus. Acetic acid is a weak acid, so that's going to stay together. Sodium acetate will split. I guess if I'm writing them, I'm writing them. Yeah, and then water. 2Na plus 2C2H3O2 minus. And so really it's just one of the sodiums, one of the acetates. Oh, sorry, both the sodiums. Questions? Concerns? Quotes of the day? All right, cool. Let's see. So this one's sodium hydroxide, aqueous, plus ammonia, aqueous, plus ammonium hydroxide, or ammonium chloride. So which things react here?
I see the potential for ammonium hydroxide if we add water to the equation, and that's independent. Otherwise, no reaction. I think it's the water.
Honestly, like so few of these are no reaction. If you get one that's no reaction, it will truly be no reaction. Actually, I'm not sure. I don't think any of them are no reaction.
To ammonium hydroxide.
It might help to even just write out the net ionic, or like complete ionic for the left side. Any guesses now?
2H3 water and then salt.
Yes, so we got hydroxide. So sodium almost never does anything. Chloride will react with some things like silver and lead. There's another one I think, but I'm missing it. So really, we don't probably not going to worry about these. But looking in here, hydroxide and ammonium. Ammonium's got a hydrogen that it could lose and become ammonia. So this would be A plus 2NH3. Oh, actually, not Na plus, NaCl. So really, chloride, sodium, 1 ammonia, oh, aqueous, aqueous, Any questions on that one? Yeah. Good? Or you have a question? Here's a bit of a meta question for you. Why am I having you do 3 big, long worksheets of net ionic equations? I'm not doing it to torture you, because I remember doing them. I think these are the same exact ones that I did in Chem 1 and Chem 2. So what is the purpose?
We're going to do acids and bases.
Yeah, we're going to do acids and bases. Well, it's like, that is relevant. A lot of these are acid-base reactions, sure. Because like net ionics, complete ionic equations are useful just in chemistry in general as seeing like, well, let's narrow it down to exactly what's happening and like the stuff we need to focus on for the reaction. But in terms of like pedagogy, which is like the philosophy or ideology of like how to teach things, and maybe because some of you guys were just quiet, but for things like this where it can be hard to see what things react, net ionic equations force you to go through the motions of figuring out which things react, canceling out all the things that don't react. And so it's trying to train your intuition about chemical reactions as to which things are important and which things aren't. And the only way you can do that is by doing a lot of them and seeing a lot of different scenarios. So it's not for nothing. It's not just torture, and I will get around to grading things, I swear. All right, copper 2 chloride. Oops. Chlorides are mostly aqueous, so I'm going to assume that's aqueous. Yep. Oh, mercury was the other one I missed. That's what it was. So, something to think about on this one. Ammonia is one of those ones that, I mean, even if you look at all these complex ions, I guess there's only 4, right? There's 4 different complex ions that could form from ammonia. There's a bunch of them for hydroxides. There's a bunch of them for chlorides, too. This problem doesn't tell us if there's a lot of ammonium, or a lot of ammonia, or not a lot of ammonia. But it does tell us it forms a precipitate. Any guesses as to what that precipitate is? Yeah. It's not going to be copper and ammonia or ammonium, because ammonia doesn't have a charge, so if anything, it could be a complex ion. Chloride and ammonia, not going to do anything, so copper and hydroxide, so we have to add water. Okay, NH4 plus Cl, not plus, just Cl. Did not leave enough room. So this is going to be Dang it. Aqueous. Any questions? I am going to give the key to Jonathan and to Omar. I'm going to tell them not to respond. Don't ask for, like, if this is correct in the general. Like, if you have a question about one of the net ionics, you can ask a question of, like, not asking for the answer, if that makes sense. You should try to go to their SI sessions and ask them there, and you can just check all of your answers. Fix the ones that aren't right. Or have Jonathan check them. If you can't make it to the SI sessions, then you can send them a private message on Discord to ask and check. But it's important that you do them. And I will post digital versions of these solubility rules and the complex ions. But otherwise, the rest of the time is to work on this or ask questions on it. Or if you have questions about the test on Friday, because that's not super fair to Friday Lab.
This one.
Mm-hmm.
Since you're gonna have a copper ion
Mm-hmm.
and ammonia, why can't you use the reversed version of this to get a different answer?
Because excess ammonia is not excess ammonia.
It has the same excess.
Yeah.
Because it's got a 4. It's a lot of ammonia.
Yeah, it's a lot of ammonia. Yeah.
Like just one arrow instead of like a reversible arrow. Is that one just not reversible?
Oh, whoops. No, just force a habit.